In order to do our point distribution models, we're going to use a technique called principal component analysis. And this bit of the lecture is a review of the core ideas behind principal component analysis. Imagine that we had a set of data points in some dimension d. Okay, it could be 3, 5. And when we're looking at our t-shapes, we're going to be looking in a 16-dimensional space. For the sake of argument, we're just going to start here with a picture that's just a 2-dimensional space. And so here's our 2 coordinates, and here are some sample values that lie in that space. So we've got our points x, that's right there. They have a mean value at some sort of point here in the middle, something like that. And we're going to want to do principal component analysis. What that really means is taking a look at that data set and finding a set of new natural axes that somehow describe that shape, the shape of this distribution right here. If you can look at this distribution right here, you can see, well, although the coordinate axes that are given for the original description, here sort of horizontal and vertical, leave all the data in a kind of diagonal sort of noisy swath. If instead we had coordinate axes that lay in these 2 directions, we can kind of see that they actually align with the data. And that's really the core idea of principal component analysis, is to take a set of data and find the axes which describe the natural directions of variation of that data. Once we have those axes, we can then talk about what the position of that point is in the new axes. So if there's any one of these points x, which originally was represented using these 2 coordinate axes, we can now re-represent any point in here with respect to the new coordinate axes right here. Here we can sort of see how that's expressed. Here is the original point in its coordinate axes, and we can express that by taking the mean coordinate plus some sort of offset based on the 2 coordinate axes, sort of a1, sort of a little bit along a1 and then a little bit along a2, and then that gets the point right. So that little bit that I used right there that's these w terms right here. Those are the weights. Okay, so that allows us to say, take a point that was originally represented in this space, and we can now represent it inside this principal component analysis space with the new coordinate axes. Well, the tricky bit here is actually finding where those axes are. And that's what we're going to go through here. We're going to do it in 2 ways. First, we're going to do it in a geometric kind of way so that you get a kind of a feeling for what's going on, and then we're going to do it in an algebraic way, which is the way that everyone does it because it's nice and easy, and also MATLAB has all sorts of built-in algebra that allows you to do it quickly, and in fact even has functions built in to do it for you. Well, if you remember back to our coordinate representations, we talked a little bit about coordinate transforms and rotations and translations. We're going to use a little bit of that kind of idea right here. Our problem of transforming these original coordinates in x into the new coordinates, this weights w, it's actually quite a straightforward thing. We're going to take this formula right here and exploit a property of these new coordinate axes here, a. And that property is given right here. There's actually the 2 of them. Any 2 of these coordinate axes, if they're not the same axis, if you take the dot product between the 2 of them is equal to 0. That means that they're perpendicular to each other. That's sort of normal for coordinate system axes. And we've also arranged for all these axis vectors to be unit vectors. So if you take the dot product with itself, it's always equal to 1. And that's all we're going to need to be able to do that. So if we took that formula that we had previously, and we want to find these weights right here, the question is, how are we going to find that weight? Well, it's quite easy. We take that formula that we had before, we subtract our mean vector, which we've calculated previously, and we dot product it with one of the coordinate axes. Okay, and that's sort of the key trick step, is to use this form right here. And if we take that formula that we had just a minute ago and substitute it in for the x right here, subtracting the mean, that gives us this bit right here. And we take our vector right here, we can move it inside the sum. So we move it right in here. And now we get the dot product with this ak and that vector right here. And we can use this property right here that says almost all of these are going to be equal to 0 except for the one when the 2 indices are the same, when the j is equal to the k. And then that's equal to 1, so therefore the sum kind of disappears just down to the single coordinate right here. So that trick really means that we start with dot producting effectively with that coordinate axis. We get the weight along that coordinate axis that gives part of the new coordinates. So that's the kind of trick that we need to do to transform our original point into our new coordinate system representation. So now with that idea behind, now we can do our principal component analysis. Okay, so here's our data set, here's our coordinate axes. And the first thing we're going to do is we're going to find the axis which goes through all of those data points. Okay, so there's our axis A1. And then once we've got that axis, and it's going to go through the mean point here somewhere, then we can project all of these original data points down onto that axis. Okay, to giving us a subspace that's sort of perpendicular to this space right here. So there'll be a little sort of clump of values all sort of projected down on that. Once we've got that, then we can go and look for the axis of all the remaining data values. Okay, and we can do that again using the same kind of method, except for now our dimension is one smaller than we had previously. And we can keep on doing this until we've mashed all the data points down into a single dimension. Okay, and we can find all of our new axes. Now I kind of glossed over how do we actually find this axis right here, and we don't really need to do that here, because what we're going to use is a simpler way of doing this this principal component analysis that's always been already all packaged up for everybody, and that's what everybody does, so we don't really need to kind of go through all the details of it. Okay, so why do we want to do that? Well, first of all, having a principal component axis gives us a kind of natural description of the object. It says the natural variation of the object lies along this particular direction, and maybe this other direction is just noise. And if we make that assumption, that really gives us two different advantages here. One is that we could, for example, get rid of all of the noise just by projecting it down onto that axis, so we're left with all the values with its natural variation. We've kind of ignored all of the other sorts of things that we don't need. Okay, it also gives us some idea of what are the natural directions of variation of the object. In this particular case, it says really there's only one natural direction of variation, and that's this one right here. When we look at our T-shapes, we're actually going to find that there's more than one natural direction of variation. But although we're going to start with a 16-dimensional space, we're only going to find about 5 directions of natural variation. So we're going to say that there's 5 ways it can vary in a sensible way, and all the rest, the other 11, are going to be just noise directions. We can just ignore all of those. So this gives us our two advantages. One is we find out what's the important ways it varies, and also tells us what's unimportant about the data, and therefore we can ignore it. Well, let's do this PCA the more algebraic kind of way. That's the way everyone does it. In fact, the way everyone really does it is they use MATLAB, and they just use the MATLAB function. But if you don't have MATLAB, you can do that a little bit more piecewise. So here's our data points again. They're in a d-dimensional space, so each of these is a d-dimensional vector. We've got n of these. We need to find our mean vector. That's m right here. Just in the usual sort of way, we add up all the vectors and divide by the number of them. We need to compute something called the scatter matrix. So there we take the mean vector and subtract it away from each of our data points, and then also got our transpose. When we multiply these together, this will give us a d by d dimensional matrix, and we sum these up over all the data points. So that's our scatter matrix X. We apply what's called singular value decomposition. That's a general sort of matrix manipulation technique where we take that S matrix and we can decompose it into the product of 3 matrices, a U matrix, a D matrix, and a V matrix. So D is a diagonal matrix. And then finally, our principal component analysis gives us for our A vectors, the ith principal component is the ith column of this V matrix that comes out of this manipulation. And we also get a measure of how important is this axis, and that's the ith eigenvalue of this system right here, which is also the ith value which is on the diagonal of this D matrix. So it gives us a bunch of useful information all at once right there. And we'll see how to use that later when we look at the point distribution model. Right, so this little review of principal component analysis has given us some idea of both a kind of geometric understanding of what principal component analysis does, and a little bit of an idea, a little bit of a hint as to why we want to do it. And we've also looked at a kind of a practical algorithm for doing this using a little bit of algebraic type manipulation. And what we'll see next is how we can use all of this principal component analysis as part of a point distribution model. Thank you.